Good evening, everybody. Today we're going to take a look at part of Chapter 11, and we're going to do some more investigating on the different types of chemical bonds that exist. We've just finished our study of compounds with ionic and covalent and acid compounds, and you just completed a lab on learning about the different properties that ionic compounds and covalent compounds have. Well, in this chapter, we're going to start looking specifically at the bond between two elements, regardless of how many elements are in the compound. If you take a look at these descriptions here, or these illustrations, you'll see that there's a tug of war going on for electrons. And if you look at the elements involved, chlorine and hydrogen and hydrogen and hydrogen, these are covalent bonds. We have some more details to get into with our covalent compounds. Of course, we still have our ionic compounds that we will address, and here is where electrons are not shared in any way, shape, or form. There's no fight, it's just a donation exception type of a situation. Before I even talk about this slide, please stop and copy it down. You need this graphic organizer in your notes. Got it? Good. All right. So we've learned about ionic compounds. We know that there's a metal and a non-metal and electrons are transferred. We know covalent compounds have shared electrons. However, we are now going to classify a covalent as either a pure covalent or something that we call non-polar, or a polar covalent compound. Take a look at the difference between the two. In covalent or non-polar covalent compounds or bonds, the electrons are equally shared. In polar covalent compounds, the electrons are not equally shared. We need to look at something called electronegativity. You're going to investigate electronegativity tomorrow in class, so I have to kind of walk you through it a little bit here tonight. Electronegativity is the affinity that an atom or element has for electrons. Affinity here means that atom wants electrons. Electronegativity increases as you go up a group and across a period on the periodic table. Fluorine has the highest electronegativity, francium has the lowest. I want you to take a look at some electronegativities in this electronegativity table here that I've got. Take a look at this. As I just said, fluorine has the highest electronegativity, and although it's not listed here, francium is in the opposite corner down here. It has the lowest. It's typically a 0.7. Notice these numbers have no units. Electronegativity is a unitless measurement. You guys are going to love this. Okay, let's take care of that writing and put this guy back down here because you don't need it yet. We can determine the bond type by looking at the difference in electronegativity of the elements involved in that particular bond. If the difference is 0, we consider the bond to be covalent or non-polar covalent. If the difference is less than 2, we consider it to be polar covalent, and if it's greater than 2, we consider it ionic. You have an electronegativity chart on page 320 in your book. You do not need to copy it down. It's there as a reference for problems, and for any assessment I will give you an electronegativity chart. Okay, let's take a look at 3 examples. If we first just try to classify these compounds the way we already know how to do this, HF is going to be an acid because of the hydrogen. Cl2 is going to be covalent because it's a bond of non-metals. NaCl is going to be ionic because sodium is a group 1 metal. Let's see if using the difference in their electronegativities confirms what we already know. For HF, the electronegativity of hydrogen is 2.1, and we need to find the difference of the electronegativity for hydrogen as well as fluorine, which is 4.0. Now, there are no negative answers, so we kind of use the absolute value option from math. And when we use the difference, or when we calculate the difference between these two electronegativities, we get a 1.9. 1.9 is less than 2, but greater than 0, so we would consider this bond to be polar covalent. Now, we know acids are covalent compounds already, so it works. And we also know that acids act like ionic compounds, so the fact that the difference is almost 2 and almost ionic really makes sense here. Let's take a look at the chlorine bond. Chlorine has an electronegativity of 3.0, and I'm looking at the chart down below. 3.0 minus 3.0 is in fact 0. That makes this nonpolar covalent. We already knew that chlorine was covalent because there are no metals. Finally, let's take a look at sodium chloride, NaCl. Sodium has an electronegativity of 0.9, and chlorine has an Chlorine has an electronegativity of 3.0. When we do that difference or subtraction, we get 2.1, which is greater than 2, which is ionic, which we knew because sodium was a metal. The reason why we're interested here isn't really to decide whether something's ionic or covalent. It's more of using electronegativities to decide if a covalent bond is nonpolar or polar. So what do we do once we've identified a covalent compound or bond as being polar covalent? There's some things we can do to identify this. Let's take a look at that the hydrofluoric acid, and we have a bond here. We actually designate the bond with this dash. A dash equals a bond, okay? We'll get more into that in another lecture. Anyways, the electronegativity of hydrogen, if you recall from the last slide, was 2.1 and 4.0 for fluorine. That means fluorine wants electrons more than hydrogen. So the way we designate that is with this little letter right up here. That is the Greek letter delta. It's basically 3/4 of the number 8. Now, what charge are electrons again? Negative, right. So the fluorine has a center of negative charge, and we designate it with a delta negative. The hydrogen doesn't really want electrons as much as fluorine, so it becomes a center of positive charge, which we designate with a delta positive. An alternate way for us to designate the polarity of the hydrofluoric acid bond would be to draw an arrow showing where the electrons are going to head, and then a little plus sign over here at the end to show that the hydrogen has the center of positivity or positive charge, and the fluorine has a center of negative charge. Just to summarize real quick, this whole lesson about electronegativity was important for us so that we can determine whether or not a covalent bond is polar or nonpolar. We're further classifying covalent bonds as being polar or nonpolar using electronegativity.